Good morning everybody, and this is the last class regarding Fourier transforms and convolutions. After that you will have a series of set of lectures from the Sobolev spaces, because your background is everything is now complete. You have studied enough material, at least from the as a first part of the course on distribution theory and Fourier, the material required to understand your Sobolev spaces. So, let us start with an example. One more example. Okay. So, I was commenting in the last time, there are distributions where you can take the triple products, but then it may not satisfy the associative law. T1 equal to 1. So, simple example, T2 is equal to delta prime and T3 equal to H. Okay. Note that T1 and T3 does not, so only one has compact support. So, it is not violating the results we have proved about the. So, having two of them having compact support is here, only one of them, only T2 has compact support, only T2 has compact support. But then 1 H are all functions locally integrable, and it is all defined temporal distribution. So, you and also convolutions can be defined. Okay, these is all temporal distributions and convolutions, just let us see. So, let us compute my T1 star T2 T3 star T3, that is equal to 1 star delta prime star H, but then this is 1 star. Okay. This you can take it delta prime to 1. So, with derivative of 1, that will be 0. So, this is nothing but 0 star H, that is equal to 0. And on the other hand, if you compute the other one, T1 star T2 star T3, that is equal to 1 star delta prime star H. So, you take the derivative to the other one, that is why you can take the derivative you like it, whichever side one you want it. So, it will be 1 star delta star H, and that one 1 star delta star H is what is delta star H, and that is delta, right, because delta prime. So, sorry. So, that will be derivative will go there, and then you will get a delta star, and H prime is delta, you see, and delta star is delta, 1 star of delta, and that is equal to 1. So, you see, so both these two things are not equal. So, we want to some important things which you have here, and some remarks which you have already seen, but I want to again and again how the convolution looks like. You already seen that DRN is dense in, so making some remarks. Okay. DRN is dense in, which we are already seen, okay, dense in repeatedly LP of Rn. Of course, for 1 less than or equal to P less than infinity. Okay. Now, suppose F is in LP of omega, okay, and omega open in Rn. Then you define F tilde as the trivial extension. Maybe it is commented earlier, but let me, for the sake of completeness, in Rn minus omega. Okay, this would have seen it also. So, which is in LP of Rn. Okay. So, that implies, by this argument, this implies there exists Fm in LP of Rn such that Fm converges to F in LP. Okay. No, F in D of Rn D of Rn such that Fn converges in LP. So, you see. So, you can restrict L thing. So, that is immediate then. Once you that Fn restricted to F converges to, this is in Rn, F tilde, okay, Rn F in LP of omega. Okay. So, that means your C infinity of omega bar is dense in, this is actually in LP of omega. I said this we already seen, but you can actually prove, which we have done, but in other preliminaries and other things you can actually show that d omega is dense in. Little more calculation required. I think probably it is done in LP of omega. Okay. So, just make a remark here. So, with that I want to prove something else, some theorem. This is some simple theorem. This is about distribution now. Let T is in D prime, okay, D prime of course Rn, equivalently respectively, or T is in E prime. Okay. Then, so you see how even the bad distribution, it will be very irregular, right, more than irregular functions. T star of rho epsilon, whatever we have studied now, this is used it, but now you exactly see that T star of rho epsilon is C infinity functions with the compact support, hence T star of rho epsilons are modifiers, many times we are using it, modifiers. Okay. And this is in C infinity of Rn, or respectively, you can say that respectively. So, respectively it is in D of Rn. If T also has compact support, you will have T star of E will be in T of Rn. Okay. And this will converges to T. I told you there is a strong topology which we comment. The weak star topology is that some families converges to that for every phi. Tn converges to T means Tn of phi converges to T phi. The strong topology, we make some comments at that stage that this converges uniformly on bounded sets of D of Rn. That defines actually a strong topology, though we did not give the details thing. So, T star of T converges strongly, you see, strongly in D prime. So, you have a family of functions, C infinity functions. So, you are given a distribution, you are able to find C infinity functions, and then treating that C infinity functions as distributions in the space of distributions, you get an approximation of T given by the distributions generated by C infinity functions. That is a kind of a powerful tool. Okay. That is T star of rho epsilon at phi converges to T phi uniformly on bounded sets in D of Rn. You see uniformly. The proof is quick, so I thought I will give you. So you should understand these kind of. So though we started with distributions are somewhat very elements which I cannot understand, but you can essentially you already seen some local structure. You can also get approximations, very good approximations. So proof is just compute it, rho epsilon minus T. So you have to understand that phi, as I said, this is a trivial thing. So you T star of rho epsilon, by just apply the definition, features at 0 minus T star of features at 0. Okay. So that is equal to T star of rho star of rho epsilon star features minus features, okay, at 0. Now, so this is nothing but T of it's rho epsilon star phi minus phi. Okay, that is fine because chest found effect rho epsilon. Okay, because rho epsilon is a modulus function, it is a non-negative function. So it's that's fine. So now this immediately goes to 0 uniformly because rho epsilon star now rho epsilon star phi minus phi goes to 0 as epsilon tends to 0 uniformly on boundary sets. Boundary sets of D. That implies T rho epsilon converges to T strongly, that is a definition, strongly in D prime. So it is important to remember this. Okay. Okay, so with that, as I said, there is another way of defining convolution via tensor products, but we do not do it. Okay. So to a couple of important things I want to finish it, then we will finish this convolution thing. This is another interesting thing what are called convolution maps. So again start with given T in D prime of Rn. I can define a map LT, linear map LT from phi belongs to G of Rn to E of Rn, that is a C infinity function by LT of phi is equal to T star of phi. Okay. This is called the LT is called convolution map, called convolution map. Okay. So the interesting result is that the theorem is that LT commutes with the translations, that is tau x LT is equal to LT convolve with tau x, and or let me use probably y, both are same because in my computations I used y. Okay. L of y t L of t tau y for all y in R. Okay. The more interesting thing is the converse. Conversely, if that is a thing. So, so again it is an association with the convolution map and thing which you can expect little bit because every distribution is associated with by its convolutions. Conversely, if L, this commutation is the characterizing it, D to E is a continuous linear map, continuous linear map that commutes with all translations, commutes with all translations, then L is a convolution map. L is a convolution map. So, these are the only continuous linear maps. So, that every continuous linear map commutation is associated with a distribution. So, it is somewhat powerful, not difficult proof. So, I will give the proof. LV is a convolution map, that is there exists T in D prime such that L is equal to LT. You see, very powerful. So, let me try to give a proof. The forward part is trivial, easy. So, you just write down that. So, first part, assume. Okay, so then assume LT. Assume LT means LT of V is equal to T. Assume LT of V is equal to T star of V is given. That means T is given. Once you given a T, you can define that one. So, it is just a one line thing. So, tau T. So, you just, if you are not convinced, I will write some couple of steps. Phi is equal to T star of tau y of phi by definition. This composition tau y phi at x. So, I evaluate at x basically, okay, because LT, the composition is a D to E. So, it is a map you have to understand. So, it is a LT is a map from D to, it is not a real line. Okay. This is equal to x, and that you can see, you can write down again by the thing convolution and T is operated correctly. Okay. So, it will be tau x of tau y of phi chess. Okay. That is the definition. So, tau y of phi chess at tau x of t. Okay. That is by definition. On the other hand, tau y of LT of phi at x is equal to LT of phi evaluate tau y. It is LT of phi evaluated at x minus y. You see, tau y is takes there, that one. That is nothing but T star of phi at x minus y, and that is nothing but T of tau of x minus y at phi chess. That is a definition, and you can see that both are same. That you have to some remarks earlier I made it. This both are same. both same means this is same as this one. The definition, look at the definition of tau y of features, it will be tau minus y of features. Okay. So, this one is basically tau x of if I recall correctly tau minus y of features, that is nothing but tau of x minus y of features. So, it is both are same. So, you get the commutation. Okay. So, the proof of the converse. So, converse, if you think little bit and get some ideas, you know what operator to look for, what distribution to look for, because if there is a, if L equal to L t, t has to be certain form. Okay, you know that and that is what. So, once you understand that in the converse you have to prove that converse, what is that? Given L, okay, from D to R, E, continuous linear, and tau x is commutes, right, commutes, tau y of t, tau y of L is equal to L tau y. Okay. To prove that, so L is equal to L t for some t in D prime. What I am saying, that the motivation of the proof is almost trivial, because if L equal to L t is of phi is equal to t star of phi, then you should know that if you know L phi is equal to L t of phi is equal to t star of phi, and t star of phi you know basically. So, you know t, that is what in the right from the beginning we are telling. Once you know t star of phi, so you know that t. So, if you want that a proof that L has to be of the form t star of phi, and then your t has to be of the form t features evaluated that one. So, that is that you t you do not know, L is given. So, you define that is the motivation. Okay. That is the way you have to say. So, think little bit about that one. So, so consider, so that is what you will do it, I will complete the proof anyway. Consider phi in D going to L phi 0. Okay. So, equivalently you have to work with features. So, it is better this one, otherwise you end of it you realize it. Equivalently phi going to L features at 0, both are same. But if you start with the phi, you see that some features just is missing. So, to do that one. So, this is from D to R. Okay. This is in R. L phi is in E. So, L phi evaluated at 0. So, this is in R. So, this is a continuous linear functional now, is a continuous, that is what you are looking at it, linear, because L is continuous from D to E. So, this will be continuous linear functional on D, and that is your T basically, that is what I am trying to see. So, define T of phi is nothing but L features, this is what I said is a simple motivation to 0, L T features at 0 or T features. So, this is a definition I am giving, T phi S is equal to, both are same, L phi at 0. That. Okay. This is nothing but by definition. So, this is nothing but T star of phi at 0, that is all. Because T features you are defining, then it will be T phi star of phi at 0 if you define that one. Now, so you have your formula is at the origin to get your any. So, you have to show that L phi of at any point x is equal to tau minus x of L phi at 0. So, you see tau minus L phi at 0, Now you use the commutativity, so far you are not used. So first you prove the result at the origin and then you use the commutativity tau minus x of L phi at 0, and that is equal to L of yeah, that we have this one. This is nothing but by definition, because you already defined that one. By definition, this will be T star of tau minus x of phi, and that is what you want to prove it, and that is exactly T star of phi. This is at 0. So you see, so tau minus x will go there, so you will get that one, and this is at any point x. So first you have this here, and then you will have that L phi at 0, you have that one. So that is it. So you see, every continuous linear operator from D to E that commutes is essentially a convolution map. I have left with a few more minutes in this section. So I will just make few comments, not really comments. I will give you now a formal definition of fundamental solution. Okay. Okay. So so you already seen, if I take dH by dx in one dimension is your delta. Okay. So so that is H solves, H is the Heaviside function, H solves du by dx equal to delta. So you see, so it is an ODE, but then ODE is defined with a distribution. So you see, so you can now, since you are a distribution, you can consider this thing. Okay. And now suppose F is compactly supported. Suppose F is compactly supported and maybe whatever locally integrable function and all that, supported, locally integrable. Okay. Then what is your D? H star of F. That is by definition, this is dH star F, but dH is delta. So you have all machinery then. So is equal to F. That implies H star F solves du, means du I used distributional derivative F. You see. So by knowing the solution of these equations, differential equation, one particular solution, you are able to solve this for general F with compactly supported and all that. So so S equal to H star F is a, of course is a, in a sense of distributions we are doing it, is a distribution solution to du by dx equal to F. So this can be given a general definition now. Okay. L is equal to more general operator A alpha d power alpha of alpha mod alpha less than or equal to F. In some sense we have used it. So it is not really a definition. So the fundamental solution is a solution of this one. So the fundamental solution is a solution of L of E equal to delta. Then E is called a fundamental solution, if if solution of L, the differential operator L, if, so there are so many things. is a fundamental solution, is called a fundamental solution, of the operator, called a fundamental solution of L if it satisfies this equation, of course in the sense of distribution L equal to T. Suppose now T is a distribution with compact support, so T E prime, and then L of T star of E. You are already seen this for specific cases. Now you are with your knowledge on distributions and convolution, you can make everything in very rigorous what you are doing it. That is all I am doing. You have seen it for the special cases even in the first course on partial differential equations. So by definition all this differential operator L consists of finite linear combination of differential operator and A alphas are nothing. So you can operate on LT any place you like it. LT not LT. Okay, not LT. You can T star. You can T star of LE, and AE is the fundamental solution. So it is T star of delta, that is equal to T. Therefore S equal to T star of E solves L S equal to what do L S equal to T, yeah, just like T is here F. So you have the solutions of this equation L S equal to T for T is anything with compact support. So you use that one. So I will give a couple of examples for you to do it. So you can do it as exercises if you see that. So one we already seen that any Heaviside function, the fundamental solutions are not unique. This is a constant. Are fundamental solutions of d by dx. Okay. So the exercise you can immediately do easy find fundamental solution of d power n by d power m by dx power m. Okay, that is d power in one dimension. It's not a bad thing to do it. And then second thing, find fundamental solution of d power n by dx1 etc. dxn. We call it d power some sort of d power alpha, where alpha is equal to your 1 1 1 etc. You can do it the other things. You already seen this fundamental solution. So this is, let me recall from here, minus 1 over 2 pi. You can find more fundamental solution if n equal to 2. Now it is a 1 by omega n into n minus 2, the surface measure, into mod x power n minus 2 if n greater than or equal to 3, and fundamental solution of minus Laplace. Now you prove it, that means minus Laplacian of u equal to delta. So this is the one we were missing in the previous class. Okay. So you see our book if you want, PKN PSD PDE book. Okay. One last theorem which we you can actually show that is a direct thing. So, I will just see that if phi star of psi meaningful wherever it is hat is equal to is a. So, you see the convolution, this is the Fourier transform. Okay, let me use the term Fourier transform. So, that f of the Fourier transform of phi hat is okay. So, this I will leave it as an exercise. You write down the condition Fourier transform of f, sorry, this f and psi are always Fourier transform phi into Fourier transform of psi. Okay, I will leave it as an exercise if you want it. It is just an interchange of integrals. Okay. So, you write down the definition of Fourier transform and then make your some small change of variable. Okay. So, and this is an important formula, that is what you have to see, which extensively used in the applications. Okay. So, with this so phi psi if you want to be taken to be in the short class, so that you may not have any problems to understand that one. So, thank you very much. So, with this we will close this chapter on Fourier transforms and for convolutions. Thank you very much.